CXS stands for the Australian Research Council Centre of Excellence for Coherent X-ray Science. It's a large multi-institutional program of research exploring how coherent X-rays can be used to investigate important problems in biology.
X-rays are electromagnetic radiation and sit on the electromagnetic spectrum. The special thing about X-rays is that they have a very short wavelength, which is comparable to the distance between atoms roughly, and they're very penetrating and energetic, so that they can pass through opaque objects and enable us to see through them.
X-rays are just like visible light. If you think of visible light as having a long wavelength, and it's good for looking at things that we do every day, so it's good for looking at tables and things like that. X-rays have a much shorter wavelength, so they're much better for looking at smaller things, and that's the main difference.
X-rays are a very penetrating form of light, so that means that rather than stopping in things, they tend to pass straight through things. But sometimes they stop and they scatter, and that's very useful because they provide information on the things that they're passing through.
So if you think of light, you can think of light as being like a stream of bullets. Now, to X-rays though, light is really much more like a stream of beach balls. So they're big and bouncy and fluffy, and they bounce off things in all different directions. But the problem with the beach ball bouncing off things is it doesn't give you any detail about the thing that it's bouncing off. So if I bounce my beach ball off Leanne, my beach ball will bounce off Leanne and just sort of bounce off in a general direction. And from that I can infer that Leanne is a creature which is about 1.6 metres tall and roughly rectangular in shape. But if I take an X-ray, which is much, much smaller than a beach ball, and much more like a ball bearing or a marble, I can ping those marbles at Leanne and they'll bounce off in nice little ricochet and defined angles that depend exactly on the shape of Leanne. So by collecting enough marbles bouncing off Leanne or ball bearings bouncing off Leanne, I can build up a picture about what Leanne's shape is. And that is one of the really useful properties of X-rays. So, but in terms of defining X-rays, they're really much more energetic and much smaller in scale than visible light. As everybody knows, the sort of classical picture of an X-ray is the thing that you do when you break a bone and you go to the doctor and you get a picture of a broken bone. And that sort of picture works by X-rays actually being absorbed by the bone and getting through the skin, so you can see the bone in contrast very nicely. And we call that absorption contrast. And that's a fantastic way of imaging, and it's been done for well over 100 years since X-rays were discovered.
Our job here is to help illustrate or to demonstrate patients' pathologies. So if you had a fracture or a disease process going on in your body, it's our job to try and illustrate that with X-rays in this case. So the information we get out of a general X-ray setup, which is what we're looking at here today, this is what most people think of when they think of X-ray. Normally we get a two-dimensional image, and that is of bones and joints, and also of people's lungs and abdominal area. For general X-ray, we normally have a setup like this with the X-ray tube, the image detector, and obviously a bed for the patient to lie on if we need them to lie down for the projection.
Probably the most common use of X-rays for us is in the radiography of painting. A bit like medical X-rays really. They're images of pictures made using those wavelengths of energy, and they're transmission images straight through the whole structure of the picture. To shoot an X-ray image of the painting, we put the X-ray source in the bottom of a lead-lined box and shoot vertically up through the picture with the film sitting on top of the paint film. So it's a one-to-one image of the paint layer or the whole structure of the picture because it's a transmission image coming up through. We take the plates and then scan them and make digital files of them, and because we use more than one plate usually for an X-ray image, they're stitched together digitally. We use them for two purposes primarily, both diagnostic and descriptive. Because they're transmission images through the whole structure, they'll show a lot of information about the condition of things, so losses in paint layers or damage to canvases, tears, that kind of stuff. But they'll also show us things about how the painting's made and about how the artist works. I suppose it's most descriptive of paint layers and changes that an artist might make in a paint layer, but it can also be descriptive of how the ground layer is applied or the stretching of the weave of the canvas. Because it's an image through the whole structure of the picture, it will tell us things about all of those components.
For instance, we've used our X-ray microscopy and microtomography to solve problems in polymer processing where impurities in the polymer were causing defects. But there's a whole range of applications. Self-healing polymers is another one we've been doing a lot of work on.
Tomography, we can produce three-dimensional image of the sample. So tomo, from the word slice, from in Greek's word, and means slice. So if you have sample, for example like this, and in microscopy, you produce two-dimensional image if it exposed with X-ray, but in tomography we produce three-dimensional image of this sample.
There's a lot of applications in looking at defects in materials. So for example, people who are developing computer chips or printed circuit boards need to be able to look at their devices and look for faults. People who are welding pipes together need to be able to look at defects in the weld in pipes. People who are on a food inspection in a food inspection company use X-rays for inspecting their products to make sure that there's nothing there that shouldn't be there.
Coherence is a property of light. In particular, if you think about the laser pointer, where when you turn the laser pointer on, you get a very well-directed beam of light with a very pure colour. What that means is the light has one wavelength, one size, and all of those waves are in step with each other. That's a property of coherence. Until recently, it has not been possible to make X-rays, which is a form of light, to have that property of coherence. And so what we're about is trying to work out how we can apply those coherent X-rays to problems in biology.
It's a disease that kills, as I said, about 2 million people every year. This is mostly kids and they're mostly in Africa. It's a very serious problem and there's a real need to develop new drugs and new vaccines to treat the disease. But it's an extremely clever organism. It's a little parasite. It lives inside red blood cells. It also can be passed from the humans to other humans via mosquitoes. But it's when it's in the human that it actually causes the symptoms of the disease and obviously when it kills you. And what it does is it gets inside your red blood cells and grows, but it actually changes the properties of the red cells so that the red cells, instead of whizzing around in the bloodstream, actually stick in particular parts of your body, and particularly they adhere inside the little capillaries in your brain. And then when they burst out of the red blood cells, then they create this massive sort of immune reaction inside your brain that causes you to go into a coma, and very often the kids don't recover from that coma. So that's how malaria kills you. And there's various ways of treating it, but there's not very many ways of actually curing it. Once you've actually gone into that coma, effectively, there's very little chance of coming out of that. So what we're trying to do is to work out how to stop the parasite from either getting inside the cell or stop it from changing the cell, and then we're going to try and use that for new drugs to actually treat the disease.
When you start to look at things like cells, there's no convenient bone or high contrast material in cells. And the X-rays will generally just gaily shoot straight through the cell and you'll see nothing on your detector. So one of the ways that we're trying to improve imaging is looking at this idea called phase. And you can think of this like refractive index. You know, when you put a stick into a swimming pool and the stick goes in and then all of a sudden it appears to bend as it goes through the water, and that's due to the refraction of light bending as it comes out from the water into the air. X-rays will actually do the same thing, but to a much, much smaller degree. So they will actually bend slightly as they go through a sample, and then that will redirect the light and give you some contrast, and this is called phase contrast. And we've been working on many different ways of phase contrast imaging, and the coherent refractive imaging is one of those methods. It's kind of the Rolls-Royce standard in terms of the small size of features that you can get to.
More recently, it's been possible to use these ultra-short laser pulses to produce coherent X-rays ultimately we'd like to be able to look at biological molecules, biomolecules.
Obviously the centre's big on X-rays, and really important thing there is to have high coherence. And so one of the things that we're doing here is to look at trying to get a really, really high coherence source. Instead of X-rays, we're using electrons. So the basic setup sort of looks like you're going to have a little biological protein here. You're going to get a whole bunch of electrons and you're going to whack it really hard and you'll get this big diffraction pattern. Really what we're looking at creating is a tool for the biologists. If they can go and image these proteins, then they can go and figure out how they work. And then one of the real big things is that you could then go and use drugs to target these different molecules. So in drug development and biology is really where it's looking at going.
The difficulty is that there's a vast number of proteins that simply won't make crystals. And the project that the centre is working on at the moment it's trying to determine a way in which you can find the structure of a protein without making that crystal, just getting an individual molecule, shining light on it, collecting the diffraction pattern, and then inverting that diffraction pattern to give you structure. If we can collect the diffraction data, it will be actually a very efficient and a very general way of determining molecular structures.
We're certainly not alone in this field. In fact, there are probably 5 or 6, if not more, laboratories around the world exploring this general area of research. And of course, as with all science, we're quite competitive with them, but it's a friendly competition, so we do share results with each other, we collaborate with each other, and we take pleasure in other people's successes, but we take even more pleasure in our own successes, of course. And so, because it is that collaborative enterprise, I think it's probably fair to say we're all about equally far away from success. We're all trying hard. We like to get there first, but I think we're all jostling for position at all times.